We have the chance today to receive Jean-Philippe Uzan. Jean-Philippe Uzan is a director of research in theoretical physics for CNRS. As a specialist in gravitation and cosmology, he works at the Institut d'Astrophysique de Paris. He was also the deputy director of the Henri Poincaré Institute from 2013 to 2017. He has published over 100 research papers on different aspects of cosmology and received both the Paul Langevin and Georges Lemaître Awards in 2010 and 2015. He has taught at the prestigious École Normale Supérieure and the École des Mines à Paris. He has contributed to the development of the AIMS Network, African Institute for Mathematical Sciences, and is on the advisory board of its scientific committee. He contributes to the dissemination of knowledge through his many books for the general public and documentaries. Which is very important to mention that in addition to his research, he is working on exploring the porosity among different fields and works with a number of artists. From 2005 to 2010, he collaborated in the different writing and staging approximately 100 performances of the play Kant. In 2010, jointly with composer Ladoire and plastic artist Van Geeschoot, he designed the installation Vodstock, which was incorporated in the collections of the French National Conservatory of Plastic Arts. His musical wanderings have continued with the composer Waxman. In 2014, he crossed past the universe of Smith at the Frénois Center for the Contemporary Art of Renoir, which was the beginning of a joint cosmic reverie. The result of this collaboration with composer Petit is currently featured at the Palais de Tokyo. His latest book, L'harmonie secrète de l'univers, describes the shared history of the music, cosmology, and math. This nighttime activity gives him the opportunity to explore the relationship between science, society, and cultures, opening up opportunities for new ways of talking about science. Please welcome Jean-Philippe Uzan.
So thank you very much for these words. It's always very embarrassing when you hear these kind of things and you are in the room. But so when Xavier invited me to talk to you, he told me, well, you have to tell, I said, what do you expect from me? And he said, well, tell just about what you have been doing. And then I started to think about what I've been doing, and I realized I never chose to do anything, just things happened. And sometimes when I have new students and they want to do research in theoretical physics or in cosmology, they ask me what it is to do research. They want to understand how do you do research. And then I realized I cannot explain what it is to do research. And I tried to make them understand that, and I told them, you see, this is like learning how to ride a bicycle. Because 2 minutes before you know how to ride a bicycle, you don't know how to ride a bicycle. 2 minutes after, you know how to do that, but if you are asked to explain someone else what it is to ride a bicycle, you can't explain. No one can explain. There is no book about how to ride a bicycle. The only thing you can do is try. You can fall many times. You can hurt yourself. You can start again. And sometimes, something happens in your brain, you don't know what. No one knows what it is, and you can ride a bicycle. So what I will do today is a little bit this. I will tell you what I've been doing. So basically, I will tell you about my life. So it could be boring for some persons, but I'll try to tell you a little bit about research, what I've been doing and how I've been doing research, and also all these other activities. And I will try to explain why, for me, there is no boundaries between my research activity and this game I'm playing with different artists. So to start, I want to start with a word. A word. Cosmos. Do you know this word? Do you know the meaning of this word? Okay, yeah, I will not ask questions because we are too much in the room. But cosmos, for those who have been doing some philosophy, they know this is what is opposed to chaos. So this is the order opposed to the chaos of the world. There is another world because you know that cosmonauts, cosmology, so it means also space, the universe. And for some of you, you know that it's also the world that is in cosmetics. So there is this idea of beauty. This I realized very late in my life, probably 15 years ago, yes, exactly in 2001, because in 2001 I was going to Cape Town in South Africa for the first time in my life. And I arrived at the border, and you know, when you want to cross the border, you are asked, why are you coming here? And I said, okay, I'm going to a conference in cosmology. And the guy at the border just asked me, do you have samples? And of course, yes, you have understood. So I was coming to a conference on the universe, and he asked me samples because he thought I was coming on a conference for cosmetics. And funnily, my book on cosmology, which is like for Master 2 level, which is 800 pages with 20 equations a page, is sold also on website where you can buy, you know, things for your lips and everything, which I found completely hilarious. So cosmos, why does this word means the universe and beauty? Why do we have the same word, the same Greek word for these two different things? And the reason is that you have to go back to the origin of this world when it has been chosen to talk about the starry night. It was chosen, and this is a legend, of course, by Pythagoras. Pythagoras chose the world of cosmos to describe the sphere on which you had the stars, because at the time people thought that the Earth was at the center of the universe and all planets and all stars were turning around the Earth in 24 hours. And he called that cosmos, because of course it was the order of the world, it was the boundary of the world. There was nothing behind this sphere, nothing after these stars. But then he explained, you know, I chose this word because cosmos has another meaning. This is in Greek, in ancient Greek, the word for the jewels that the Greek women were. And he tells us that when he looks at the sky, the feeling he has is the same that when he's looking at a nice woman wearing his nice clothes and his jewels. Okay, so this is something very important because it means that when you look at the stars in the night, of course you want to know something about the universe, but you have a feeling. I mean, there is a kind of vertigo when you look at the stars. If you have not experienced this vertigo, the next time you go in a field and there is a star, you have to lie down on the grass and look at the stars and forget that you are on Earth. And just imagine you are a small magnet behind the Earth. And this is gravitation who is keeping you stick to the Earth and you don't fall to the universe. And if you don't experience vertigo, just write me a mail because you have a problem. Okay, so this is the word cosmos. And then I went to study cosmology, and that also I don't know why. You know, I was born at the end of the 60s, so in the 70s, and at the time, humanity went to the moon for the first time, so I was a big fan of Neil Armstrong and all these astronauts. I wanted to be an astronaut or a cosmonaut because I was born in a suburb of Paris. At the time, it was called the Red Suburb, so they were all communists, so we were cosmonauts, not astronauts. Yes. And I wanted to go to the moon. So here is the moon. This is a picture I took a year ago in Lebanon with my iPhone and a small telescope that I put in Beirut to let people look at the moon, to explain that whatever our religions, we just see the same moon, you see the same shape, and they can take pictures with their iPhone. And I realized that during many years, there was no internet. There was no book on cosmology or the universe in the library. And so basically, I just had the possibility to dream about the universe and to want to study that. And finally, I just could do that when I was around 20. So I think this is very important for two reasons. The first is that here, all of you are very bright students. I mean, you are in this school, you have been selected and so on. So you have the chance to study and to be here. I was raised in a suburb. At that time, there was hope that education can change the world. And, you know, my parents, they never did any study. And I was the first in my family to be able to go to university and everything. And that was possible because we had faith in school. And I think today, when I'm going back to this kind of suburb, this is no more the case. I see children who say, I cannot. When they say I cannot, it's not that they don't have the ability. They cannot project themselves as being a researcher or an artist. So we have to go and tell them this is possible. You have to work, of course. It's difficult. And I think this is the kind of responsibility that you have when you are bright students, also to tell other younger kids in places over the world or in suburbs that they are allowed to do that. So I think everything started for me because of this. I had the feeling that because I was very lucky to be in a society where school was very good and that I was able to do to university and even become a researcher at CNRS and everything, even though my parents never studied. that I have to give back something. And it started that I wanted to explain what I was doing. I was working on cosmology, on equations that no one in my family or my friends were able to understand. I was unable to communicate with them. And then over the time, I decided that I had to try to explain to people. And then I started to do popular science. At the beginning, I was very bad because you don't know how to explain. You have to experience. You have to fail again. And I wanted to present you 3 things that I've been involved in which are very close to my heart. The first, and Xavier told about it, is the AIM Center, so African Institute for Mathematical Sciences, that I've been involved for about 15 years now. And we are developing centers of mathematics and application of mathematics in Africa. And we take students from 5th years after university, and they are allowed to come there to study. And the brightest, we try to find a way so that they go and do a PhD in the USA or in Europe. And we see we have now 6 centers, South Africa, we have Senegal, Cameroon, Ghana, Tanzania, and Rwanda, which opened just a year ago. So this is something. You can give time to study for free and meet new students, and some of them, they may be bright students. And you know, what we want to say with this is the next Einstein initiative. So there is like this dream that the next Einstein will come from Africa. Maybe, maybe not. But we have to try to give them the opportunity, because most of these kids, they don't have access to internet the way you have, to libraries the way you have. Then there is this association, and then you can contribute, les petits cueilleurs d'étoiles, with friends. We are going to hospital, and you see, this is me. I'm just with my cosmonaut. I told you I wanted to be a cosmonaut. Okay, this is an astronaut because this is from the NASA. And we go to hospital, and we see kids who are locked in hospital for months, for years, and to tell them about the universe, because the best way to dream of being free is to dream about the universe. You can go out, you can dream that you are on another planet, on other possibilities, and we bring them some meteorites, some stones coming from the stars, so that they keep this with them in order to be able to still dream. Because when you are locked like this little girl called Oceana in a room, she has been there for 8 months, she cannot go out. How do you still dream? What do you use to dream? And if you have a small stone coming from the universe there, maybe you can dream that one day you will do something like that. You will go somewhere else. You have to find ways to go out. And then I wrote books. So this is when I started to explain things. First, my first books, they were completely, no one can understand them. There was too much equations. And then I decided the best way to make me understood is to write book for children. So I wrote 2 books for children, one on gravitation and the other on the universe. This is Aura, the snail of space, which I use with my kids every night to tell stories. And he's exploring the universe and learning a lot of things about the universe. And these books, they have been designed in a very particular way, because I went to a classroom for many times, and kids were asking questions. So I started from the questions of the kids, not about what I wanted to tell them or to teach them, but about the representation they had in their mind, the question they had, and from the list of questions, I tried to write a story, making explanation, giving answers to their question, and then of course I gave the text to the teacher, and you know, they were horrible. They criticized everything, like, you cannot use this word, this is not possible, it doesn't make any sense. And they were right, because I was 30 years old, they were 9 years old, and you don't see the world in the same way. And before you try to teach, what you have to do is to understand what is in the mind, in the head of your students. How do they see the world? Because before you try to put new concept, you have to understand the way they see things, so that you can deconstruct what is in their head if it's not correct. And this was a very nice experience. And then for a couple of years, I was this character in this Cosmic, which was in La Revue Dessinée. And I think it's pretty good. So we had a lot of fun. I was trying to make fun with science and explain that science is all over here. Science is technical. Most of you, maybe you are not, attracted by science. You see, it's equations, it's mathematics, it's complicated. But before being equations, it's phenomena in the world, and it's all around us in the world. So we have to live with science. And I think having a culture in science is something very important. Scientific culture is part of culture. And this is what we try to push by this idea. So I was talking about equation, what it is to do science. Let me give you some equations. Okay? I'm sure you understand what this is. Okay? Who knows what this is? Just no one? One. Okay, so this is the theory of electromagnetism discovered by Maxwell. Electricity, magnets, and all these things, they are described by this set of equations. I don't want to explain to you this equation. I just want to make 2 comments. The first of it is that this is the way Maxwell wrote this equation in 1881. This is the way it was written a couple of years later, and then by Einstein, and then today. Today you can write all this equation in just a couple of letters, or with symbols. When you discover that, you ask yourself, why is it? I mean, I thought like they were just mathematics and equations, and why can you write like this long list of equations in just a couple of symbols? Well, because in about 2 centuries, we have understood the structure of this. There is some things that you don't see in these equations, which are some kind of geometry, some kind of, what I would say, beauty and structure and symmetries. When you understand that, you can unify everything to write this equation in this form. Now, when you understand, of course, you have to understand what this small d here means, what this star means, and it will take pages to learn what it is. But once you have understood that, you realize that there are things in the universe or in nature that you are not able to see if you write this equation in these things. So mathematics is the way to question the world and to make things which are invisible visible to your mind. And it's also very important because Maxwell was a very good mathematician, but he was put on the way to this equation by someone which is even more important than him, who is called Faraday. And Faraday, he realized, he was asking the question, why a magnet is turning? What makes the magnet of my compass turn? And he realized there should be something. He called that a field. A field is like the magnetic field. Everywhere there is a magnetic field. We don't see it, we don't touch it. Before Faraday, no one had the idea that everywhere there was such a field. He discovered something and he made everyone agree that there was something in nature that we were not able to see. And I think one thing about doing science and physics in particular is to say and try to answer, what is the world made of? This is very important. The second thing is that this is a set of equations. I have learned this equation when I was in preparatory school, just after my baccalaureate. And most of my friends, they were, and I also, we were used to use this equation, solve them for many problems, and to be able to make applications. My main concern when I was there was the question, how did Maxwell do to write this equation? Of course, as I told you, I wanted to go to the moon, then I wanted to become Albert Einstein and all these things like every kid. And I wanted to write my own equations. And I asked myself, how can you write such an equation? Where do you start from? I mean, you are in front of your desk with a pen. How come can you have the idea to write these kind of things? And then I realized that what I was interested in is not how to use equation to build, a radio or computer or whatever. I was interested by what the equation don't tell you. How do you discover the equation? When are they valid? And how can you write new equations? So basically, what is the nature of the knowledge that these equations are telling us? And this is what I was interested in. And I think this is a big difference between someone who wants to become, let's say, a researcher in fundamental physics or someone who wants to become an engineer. You solve the same equation, but not with the same question in mind. You don't want to use this equation to create something that you can use. You want to see this equation to say how much can you go behind this equation to learn more things about the world. So basically, when you are a researcher, you want to live in this small edge between what you know and you can master and what you don't understand. This is why you are always depressed, because you look on the right, you understand everything, it's boring. You look on the left, you don't understand and you feel stupid. Every researcher is kind of maniaco-depressive. All my friends, they are maniaco-depressive. Sometimes they are very happy and then they realize that everyone understands that. And then they look on the other side and say, but no one understands that and no one will ever understand. It's too complicated. And then you see people who are Nobel Prizes and they understand that and you don't, and you are depressed. And this is just living on this path, and you have to learn to live on this path. So basically, doing research is asking stupid questions. And that, it turns out, because I'm very stupid, I was very gifted at asking stupid questions. I will give you one example. In physics, you have what we call constant, fundamental constant, like the Newton constant for gravitation and so on. So you have met them when you were at school. I asked the question one day, are the constant? And if you look to the dictionary, the definition of fundamental constant is something that does not change with time. So basically, the question was solved. And I asked the question, and there were many reasons for asking the question, and I write, like you see, many papers, but this one, for instance, which has been cited more than 1,000 times. And I realized that if you ask this question, it means that you have to understand that the definition in the dictionary is not a good definition, because otherwise there is no question. But if you ask the question, are the constants varying, and you make sense out of it, you can create a new test of general relativity, of something which is at the heart of Einstein's theory of gravity. just by asking a stupid question. Of course, then you have to put the mathematics behind, you have to define every word. And then with one of my friends, I wrote this thing C, which is the letter for the speed of light. We say, is the speed of light, isn't it? Because if you ask any teacher at school, they would say, yes, this is 299,000 kilometers per second. This is the speed of light. And we ask, is it really the speed of light? Or is it something more fundamental than the speed of light, which turns out to be equal to the speed of light? And we wrote this paper, and it was a big success also. So because we asked stupid questions, things that you have learned at school, people tell you, this is the speed of light, the value is such and such. Really? How do you know that? And if someone tells you that it's like that, you have to ask the people, how do you know? How can you prove that this is what you are telling us? And I think doing science is just that. It's always taking the time to check everything. And each time you use a word, you need to spend time to define this word, to make your question meaningful. And sometimes you will see that there are things that seem obvious to everyone, and they are not obvious, and you can use that to do a lot of science. Okay, so my word is about this. Okay, this is an image taken by the Canadian France-Hawaii telescope in Hawaii. And you see on this picture, you have like these shapes, you recognize galaxies, this is a star. And what is interesting when you look at such a picture is that you see galaxies with different shapes, different colors, distributions. And the question of cosmology is, how do we know, where does the galaxy come from? Where does the matter come from? Can we say something about their spatial distribution? Why there are different things of galaxies? This is a whole bunch of questions. All of them, they are very technical. You need to use mathematics. You need to use observation. But there is something I want to tell you about that, because I don't want to be very technical. If you look at the stars in the night, you will see the stars. You can see in which direction you see the stars. Can you tell at which distance these stars are? No, you can't. Okay, you just see a point in the skies and you don't know at which distance it is. It was a very difficult thing for humanity to be able to measure the distance of the stars. The first time we did that was in 1838, and it was Friedrich Bessel, a German astronomer. So we don't know about that. Then we can ask ourselves, are we sure, if we cannot measure the distance to the stars, that the universe is infinite? Is the universe finite or is it infinite? What do you know about that? Of course, most colleagues just assume that the universe is infinite. But if you look at the literature, you know, people were thinking about the universe much before we were able to do astronomy. And some people believe the universe is finite because we cannot think about infinity without huge mathematics. And some will tell you, no, it's infinity because otherwise it has a shape. And if it has a shape, like a box, there is a boundary, and it's stupid. Actually, at the end of the 19th century, we realized that we can have volume, which are a finite volume, with no boundaries, and maybe the universe may be like that. So at the end of the 90s, I was asking this kind of question, and we got very nice results, to the point that we make the cover of the Nature journal, which is like the famous journal in science. And this is something about the shape of the universe. It was a hypothesis that we got from some observation. And basically, we were saying that the universe is I forgot everything. Okay, it's a dodecahedron, sorry. So the dodecahedron is a solid with the face are pentagons, and there are 12 of them. And you see, it's like you can make a pavement of space with these shapes, but the shape is a sphere. Like, you know, like if you take this shape here, you can put pentagons and you can have a tiling of the sphere in 2 dimensions. This is the same in 3 dimensions. So we said it's a possibility. And at the time we were doing that, it was 2003, we have some observations which were telling us that it's very probable that it's like that. So we made some predictions. A couple of years later, after a lot of work, we were able to rule out this hypothesis. But look, what is interesting is that this is what the tabloid in England told about our work, is that because we tried to explain how to pave a 3-dimensional space with this dodecahedron by this picture, they tell us something, you know, like cosmos football shape. And then there are all these things about how football is so important. And cosmologists are telling us that football is more important than life and death and everything. It was very funny to see how these things happen. So let me try now to show you how we can think of a finite universe. Okay, this is what I want to, before I talk about art, the piece of science I want you to try to understand. So this field of mathematics is called topology, and here is a box. You see, so this is a box, is a finite volume, and you have walls. And I have put colors on the wall, so the green walls and the purple walls. Imagine that I assume that these walls are glued together. So I take my volume and I glue them together. Basically, if my Earth here is moved in that direction, it will go there and it will come back here. Exactly in the game Pac-Man. I don't know whether you still play Pac-Man. You still play Pac-Man? Yes. Okay, exactly like in Pac-Man. So, okay, so it means that if you go that direction, you're coming back here. So basically, you can go around the universe, and the universe has no boundary. We made the boundary disappear. And you can do the same with the other. And basically, you have a volume which we call a torus. And in this space, it's a finite volume, but there is no boundary. There is no place where the space stops. And you see, if I start to move the Earth, so the Earth is, of course, rotating. We know that since Copernicus. And you see, if we go that direction, the Earth comes back. It cannot go out of the box. There is nothing that exists out of the box. Okay, that was understood by the mathematicians at the end of the 19th century. And one of the questions is, can the universe be such a shape? And if yes, what is the size of this universe? So to do that, the problem is that you cannot go outside of the universe to observe the universe, to say what is the shape of this watch. It's very easy because I can go out and I look at the watch and it's easy. For the universe, I cannot go outside of the universe. You are inside the universe. How come can you tell whether the universe is finite or infinite? So let me try to make you understand that. So this is a box with another shape, more complicated, just for the beauty of it. And here is our own galaxy. Assume there is a universe with a single galaxy in the universe, a single galaxy, our galaxy. You see, it emits light, but when light is crossing to the boundary, it doesn't stop. It goes around. So basically, light will go this direction, and it will come back here. So some astronomers here will see something in this direction. So it's like if we had mirror. And so have a look. I will make now what you observe. So this is the nature of the world. And now what an astronomer in this galaxy will observe. Okay, so now we have the walls, they will disappear. Come on, it's too long. Well, it's cosmic time, so it's very long. So, okay, they disappear, and so you see all the images of the same galaxy. And if, of course, this you don't see, it doesn't exist in the physical universe. This is what an astronomer will observe. So basically, he will see a sky with plenty of galaxies. Okay? And imagine now that you have like, I don't know, million of galaxies in your box. Well, you will see the copies of the million of galaxies. And from your observation, you cannot tell whether the universe is finite or infinite. And you have to create tools, specific tools, to try to see what is the fact that you are living in a finite universe or so. So this is the kind of game we played. And to do that, to design the tool, we have to make this animation and basically try to simulate universe with these properties and to go inside this universe to get some kind of intuition of what you should look for. And this is also some kind of experiment we did. So one outcome of this work is that a couple of months after we published this Nature paper, I received a mail from someone saying, is the universe infinite? And just the message was just, I would like to talk to you. So usually I don't answer to these messages. But there was a file with a text which I read, which was like marvelous. It was a text by a Norwegian author called Jon Foss, and the text was called Kant. And it was a marvelous story of a 9-year-old boy talking to his father, and he's completely afraid. He wants to go to sleep. He cannot go to sleep because he's just thinking too much. He says, if the universe is finite, then there is a place. So what is there after the place the universe ends? And if it's infinite, I cannot think about infinity. And the father knows nothing about science. And this is the relation between the father and the son to try to tell him that, well, if you think and if you study, maybe you can master this idea and not be afraid of what you don't know. And then my friend, he became a friend, of course. When you send me a mail like that, of course, you become one of my friends. Yes, try to send me a mail, we'll see later. He was a theater director, and he wanted to take this text and to make a theater play. And we made this play called Kant, and we see we have this relation with the father and the son, and we have all these things. And I was trying to explain to 9-year-old, 10-year-old kids on stage why it is possible to have a finite universe. And we were doing like magic tricks and everything, and we played these things for about 100 times. And of course, it was a very difficult thing for me because I was much younger than today. And when my colleagues learned about the fact that I was on stage explaining topology to children in theaters with artists, comedians, they tell me, like, what you are doing is pure prostitution. You should not be on stage in a theater to talk about science. And then, I was very disturbed because, of course, I was very young. I had a few arguments. I never thought about it. And I was just thinking, no, this is very nice to be able to talk to the children and especially to their teacher, because the teachers, most of them, they were thinking, talking about infinity and topology to kids, they will not be able to understand. And actually, the experience shows that kids were able to understand. 9-year-old kids are able to understand because they have no boundaries in their head. They say, okay, it's like that. I mean, this is what you call blue or red, and we just take it for granted, and you give us rules, and we play with these rules. The teachers, they were too old. They were not able to change their minds. They were like fossilized in their knowledge. And I think for me, it was a great experiment. And then, of course, that was the beginning of my adventure with art. So science and art. And so now that I've been doing some piece with artists, sometimes I'm asked, why are you involved in the dialogue between art and science? And then I'm always very confused because I don't know. I don't know because I'm not sure to know what art means. I've been talking with artists, and the best answer they gave me is that art is what is done by an artist. And then when I ask you what is an artist, and they say, okay, you have another artist to tell you that you are an artist. I say, okay, good. So who made the first artist? And then, of course, we don't have answers. And also, they are very different in nature. Science is not something. Science is a methodology. This is a way to study nature. It's very materialistic. You want to create proofs. You want to make experiments. You may have an idea that is coming from some inspiration. At the end of the day, I'm writing an article, and everyone is able to reproduce what I've been doing, to do the same experiments. And whether I did it or some friends or anyone in the world did this, it belongs to humanity, and everyone following the same steps will find the same answer. So this is what is about science. And science reveals things about nature, about the universe, about matter, and it doesn't explain why the things are the way they are. So I think maybe the difference is that science wants to know how the world is, and I think arts wants to know how we are to the world. What is our connection to the world? What is our relation to the fact that matter is composed of particles, that there is quantum mechanics and black holes? What does it tell us to our life? And the more you learn about science, the more you realize that there is a kind of mystery at the heart of our universe. And as I said before, Pythagoras used cosmos. He wanted to say that there is emotion. There is no such emotion in science. Some people will tell you that these equations are beautiful, but it's a very educated emotion. It's a very cold emotion. You see, is it possible when you look at the stars the way I tell you, you have to do the experiment. You see, the emotion you get is not a cold and very intellectual emotion. You will get, like frisson and everything. So I don't know. One thing is important, right, that I realized working with artists is that both artists and scientists, they are drawn by curiosity. They take care about everything. They want to understand. They want to look, and they are looking at details. And they want to understand details. And they don't take things for granted. They want to understand what is their connection to the things they understand. So if we want to go further, we can ask the question, taking these two persons, I don't know whether you recognize them, are they scientists or are they artists? I was never able to answer the question. So do you know this guy? Yes, it's Leonardo. Is he an artist or is he a scientist? He's both. Okay? No one questions that. He's not going to a committee and say, are you doing science or are you doing art? It's Leonardo, and he did very nice paintings and machines and everything. Do you know this guy? Probably not. He's called William Herschel. It's one of the best, maybe the best astronomer of the 18th century. He was the first to be able to do a map of our galaxy. He built telescopes. But William Herschel was a musician. He composed about 18 symphonies. He was a good friend of Joseph Haydn, and they discussed about the universe and about music. And you can play his music. It's very good music. So is he a musician or is he an astronomer? Well, you don't care. No one cares. I mean, just people in communities do care. So can we try to understand why we make such boundaries between what we call art and what we call science, and try to see whether we can try to erase this boundary to learn more about the world in which we are living. And there is something about this connection between music and science, and for me it's like the connection between sounds and light. So see, if you take this, you don't recognize this Echo and Narcisse, Echo and Narcisse, and Echo is about sounds and Narcisse is about light. We think light and sounds are very different, but today we know they are both sounds, both vibrations. And can we just try to look at the world by the sounds in the way we look at the world by our eyes? And actually, this is what I started to do, and I was doing a project in a class in Bobigny with 10-year-old kids, and I was working with Eddie Ladouard, a composer, and we tried to tell them, imagine that the whole humanity is blind. We don't, if you look at the sky, you won't see anything, we are all blind. How come will we learn something about our universe? And then we work and we realize that, well, maybe we will just make telescopes that will transform what we observe, which is light, electromagnetic waves, in sound. And we will learn to understand things by what we hear. This is exactly what we have been doing in science. I mean, we have telescopes in ultraviolet, infrared. These are colors that we cannot see with our own eyes. But we have images of all the stars with these telescopes that transform this light in the light that we can see. So science is a way to go further than what your sense can measure. So maybe we will have created this object. And we had this idea to try to make a trip in our galaxy just by our ears. And this was Vostok, and I will show a picture about Vostok. What is important, but time is running, so I will just skip that because this is a long thing about Pythagoras, and this is probably less interesting, and I will come back to it if you want. What is important is that this connection between music and science was not the same in ancient Greece, because Pythagoras, in his work, he found connection between mathematics and music instruments, basically led to a tradition in which we believed that music is a part of mathematics. And at the time, and this followed Plato, because Plato called mathematas all the subjects which are that you need to study in the liberal education, so the education which is there to make you free. You have to learn mathematics, and mathematics can be discrete or continue. So sorry, it's in French, but you will understand that. Discrete or continue. The discrete mathematics can be absolute, so this is arithmetic, or relative, and this is music. And the continuous mathematics, they can be static, it's geometry, or dynamic, it's astronomy. Anyone learning mathematics at the time was learning arithmetics, music, geometry, and astronomy. And this was brought to the Roman world by the philosopher Boès, and this was the case until let's say the 16th century. So if you take any scientist, Copernicus, Galileo, Newton, they knew about music, they knew about astronomy, and they knew about mathematics, because music was thought as a way of doing mathematics. The distinction we do between music and science was not the same before. So what we call disciplines has changed over time. And they were able to make some arguments in the shape of music and sometimes in the shape of astronomy. And it has great impact on the way we think about the world. For instance, there is a French bishop, Nicolas Oresme, who gave an argument that the Earth cannot be at the center of the universe because the sun was at the center of the musical harmony. And of course, he's a bishop, he cannot claim that, he has no proof. But he has some intuition that there is something fishy in the way we represent the universe with these musical notes, as Pythagoras was doing, and as many philosophers was doing. And this is a hint. And some historian even tells us that maybe, Galileo, his father, Vincenzo Galileo, was a musician. And he was also heliocentrist. He believed that the sun was at the center of the universe, and many people think that his son, influenced him. And then people found that he has some writings in which he's also questioning the connection between musical harmony and spatial harmony of the planet. And he said it doesn't fit, so maybe we have to put the sun at the center of the solar system. And now some historians are just questioning which of the father or the son influenced the other, which I think is a very nice question. It's not Star Wars, but almost. Okay, so this thing we did with kids was called Vostok. And so Vostok has been composed by trying to say, okay, we have no eyes, we cannot see. We can measure everything, and we can transform everything in sounds, and we can listen to pulsars, and we can listen to galaxies, because we just transform that in sound. It doesn't mean that these planets and these stars and galaxies are emitting sounds. Actually, there is no sound because the universe is empty, and there is no sound propagating in an empty space. But we transform them just to be able to connect them with our brain. And this is what we did, and we wrote this musical piece, it's 23 minutes, that you can listen inside this cabin, which was designed by Joop van Lieshout from Netherlands. And because we have like spatial sound, you see the sound and you feel the sound in your body. And of course, you are not explained. This piece is not to explain something of the universe. It's not to do popular science. It's just to see, imagine you are blind and you are in a universe. So this is a starting point to start discussing with people. And it got a pretty nice success because people realize that you can tell things which are interesting for art just by monitoring and using science. So this was the idea of the blind astronomer, and probably you have seen the film Contact, which I liked a lot, with Jodie Foster, who is trying to listen to aliens. And today some years ago, I met with this woman, which she's called Wenda Diaz, and she's actually a real blind astronomer. So we met, she was at one of my conferences, and then we discussed, and she's blind, she's an astronomer. She became blind, she was 27. And she's actually doing exactly what we have been doing. She's transposing all observations in sound, listening to what she listened, and to study like supernovas and things like that, and to do science with that. And she's trying to work with blind kids to explain to them that it's not because you are blind and you don't have access to information that you cannot work, because today we are in a world of data. What is like the stock markets and biology, everything is just data flowing all over. We see that on our screen with curves. If you are blind, you do not have access to this data, and you can be left over. If you use these methods, but you have to teach here, you have to understand how to listen, and it's a whole education, and what she's trying to do now. You can teach to kids, blind kids, how to read, finally, data. And I think it's a very nice way. So I will not discuss that because I will run out of time otherwise, later maybe. So that was the first experiment, and then, people talk, and I met other people. And a couple of years ago, I met Fabien Waxman. He's writing music, and he's a composer. He's teacher of composition at the Conservatoire National de Musique de Paris. And we became very close friends, and he's like my twins, or my ghost, I don't know, because he's a musician. He would have loved to become an astrophysicist, and, this was like a mirror things between us. And so we became very close friends, and we started to write music. Of course, I cannot write music, so this is the way I write music. So you see, we were in a restaurant, like Japanese restaurant, you see. And of course, he wanted to know about gravitational waves and black holes merger and things like that. And I tried to explain what happened. And you see, this is a story. This is a story with binary stars, and the time is going like that. And this is a trajectory. And you see, like, I tell a story. Because if you listen to a symphony or whatever, this is a story. It's telling you something. You have to tell a story. And you have to make the people feel what you want to explain. How do you tell that a star is a giant star, red, and another one is a small star, blue? And at some stage, there is one becoming a supernova, which is disappearing, but just making like tick, 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 tick. Like, how do you explain that? And this is the game we play. So I wrote this kind of story. And then some days later, we go with him, and he's at the piano, and he's just trying, what do you think of this? And I start to tell a story, like you do a slam. I improvise on what he's playing, and he's changing what he's playing, and when it works, we just keep it, and then he's composing. And this is the way, so this is the first core of what has become the kiss of the death. The kiss of the death is what happens when you have these two black holes or stars which are merging, and basically they collide to make one single star, and they emit a lot of gravitational waves, because at the end you just have a black hole, so basically everything is dead. And this is what Fabien has done, and it's a quintet with piano. It was created a year ago, and it's basically tells exactly the story that I have written there. And of course, then he's using some kind of symmetries and so on in the way he's writing music. But this is for a quatuor, so like standard instrument. It's not electronic music. We have not transformed anything. We just started from a story. And I told him the story of what I have understood from these physical phenomena that we cannot see with our eyes. And he's trying to tell the story with music. So the third experiment with musician is this one. So this object, first, is it a piece of art or is it a piece of mathematics? Difficult. So this is a sculpture which is in the Institut Henri Poincaré in our library. This is something that was used at the end of the 19th century to teach geometry. It's called the Chalice Surface. So some people will say it's pure mathematics, pure geometry. But here is another one. So this one is also in our collection, but this drawing is by Man Ray. In the 30s, Man Ray came to our institute. He saw this, all this, we have about 600 of them. He saw them and he found them amazed by these shapes that he cannot imagine. And he started to draw them. There are many drawings, painting. It's called the Shakespeare Equation. And of course, Man Ray did that, and all the surrealists started to be interested by these objects. And now, sometimes I show this picture to people from museums and say, yes, these are pieces of art. Aha, but I thought it was like a piece of mathematics. So now it's a piece of art because Man Ray just make a drawing. Yes, so what is a piece of art? I don't know, and no one has been able to explain to me whether it's art or science, whatever. So one idea I got with Arnaud Petit, who's also a composer, say, okay, can we try to make this shape thing? And this is what we did, and it's still, you can still see that at the Palais de Tokyo until the 12th of September. So the idea was to take a quatuor, and we remove the second violin. So there are just 3 instruments. And we make this shape become the second violin. And here, this is me, I was explaining things about this surface in technical words, in every way, trying to describe the shapes. And basically, my voice became the second violin. And so we did 4 quatuors like that. And you don't understand what I will explain. And this is not what you want. I don't want to explain these shapes. What I wanted to do is that you hear the music of what it is to describe this shape in mathematical words. And to use the music of mathematical words and these meanings and the reasons that there are in this description, basically, as a voice. And you listen to that, and basically the shape is turning, so you see there are like different directions. It's because the movie was made by Alain Fleischer, and what he was using the curves that are on the shapes to dictate the motion of his camera. And so basically, all these things, so it's on 2 screens that you can watch, and you see that there are trajectories which are exactly trajectories on these shapes, and there is a kind of quatuor with mathematics and musicians. And if you don't know anything about mathematics, it looks like really like poetry. So this is what we have been doing with music. So just basically, to tell you how things happen, but each time it was like some meeting with some musician and trying to play games and just to have fun, basically. Another part of myself, which is very important, are these 2 persons. Do you know them? So this is Lovecraft, Howard Philip Lovecraft, and this is Jorge Luis Borges. So there are 2 authors. If you have not read them, you have to read them. It's very important, and they tell you many things about reality. In their universe, they start from standard words which are really common, and there is some kind of mismatch in reality, and from this small mismatch, you realize that there is a whole world that exists around us that you don't see. I love that. This is what I call soft fiction. It's not science fiction, it's soft fiction. There you start by some details which are not matching together, and you let them grow and grow and grow, and sometimes, imagination has invaded the normal world, and you realize that what you think was reality is actually not existing. They do that in their novel, and this is the kind of game I've been playing with this artist Smith for a couple of years now, and I will just give you 2 examples and show you some pictures. So the first one is called Saturnium. Saturnium is a kind of chemical element that was discovered by Marie Curie, but no one knows about it. The reason it started by this is a well that is inside our a new building that is in front of our institute. It's closed because there is radioactivity. No one knows why there is radioactivity in this well. Of course, Marie Curie, Jean Perrin worked there in the 20s and 30s. But we don't know why. And the door is locked, and I just got this picture. And I was telling that to my friend, and one day I just imagined it was the birthday of my friend. So for her birthday, what I did is I decided that I discovered a secret, an unknown notebook by Marie Curie, where she explained what is this element she has discovered, why she has not published it. And I gave that to my friend. So it was very convincing because I work with a faussaire, so someone who was doing, it's like Marie Curie. So this is the unknown diary by Marie Curie. 6 pages. I wrote like a notebook which is about 30 pages with equations and mathematics which are completely correct. And you see experiments and discoveries and where it's coming from, and this is related to the meteorite who fell in Tunguska in 1908, which has completely disappeared. No one knows where the meteorite is. I can tell you, Marie Curie got it in a way which was very difficult because it was the Russian Revolution and then the First World War, but okay, no one knows about it. So I wrote this notebook, and then of course I invent this element, which has a property to be chronoactive. It bends the direction of time. So basically, when you are in front of this element, time doesn't make any sense. So that was the beginning. It was just a birthday present. And then, of course, she loved it, and we started to, and then a couple of months later, we went to the basement. We cannot go into the well because the door is locked. But we played music with a friend of us, we recorded that and everything, and the day after, I left to Japan to work for a month at the Yukawa Institute in Kyoto, and Yukawa is someone who got the Nobel Prize. And I don't know why, I was in the office of Yukawa, and I took a paper, and I decided that I discovered a letter sent by Yukawa just a day before Marie Curie died in 1934. And I asked my Japanese colleague to translate it, so here is the letter. Come on. Yeah, here is the letter. You don't understand anything. It's normal. It's in Japanese if you don't speak Japanese. And then I send to my friend, and I don't tell her anything, just this letter. Of course, she doesn't understand anything. And then a couple of days later, what I do is I write an article by someone which is called Bogdanjo Liukuri. So you see there is kind of stupid things here, which is exactly what you will find in physical review letter. This could be, I can show that to someone who is non-specialist with a standard article in physical review letters. You won't make the difference. Of course, there are some hints that it's crazy, but at first sight, you see mathematics. This is standard nuclear physics and everything. And basically, the guy is saying, you came to the well, you make music, you disturbed me, and I was working on these things that I found from Marie Curie because of this letter, and he explaining what this element is actually doing. Okay, so I send that to her, and I don't tell anything that it's me because it's coming from Japan and everything. And some days later, because this article was very, very important, I wrote another Nature paper by Stephanie Hawking. So this is like the transgender part of Stephen Hawking. And it was very important in this kind of discussion, but I will not go into that right now, about bending the light of time, where we're making an analysis of this article and why it is changing what we think about theoretical physics. And basically, you could compare that to some people, who are pretending to do science on TV and so on. It's more correct than what they are telling us. And so the game from that, she made pictures of people who were, so here is what is in the Palais de Tokyo. So all are pictures of people who have been exposed to this element, the Saturnium. And Saturnium is bending the time, and there are many consequences. And we start to imagine all what this element can do, how it changed the world around us and everything. And this become, pictures, music, text, and it ended in a book which is called Saturnium, like that, which will be published in Actes Sud very soon. And more important, I told you it exists, and sometimes imagination can invade reality. It enters Wikipedia. You see, this is Wikipedia. There is no cheat here. The list of fictional elements, material, and there is Saturnium, which explains what it is doing. So, you see, you can have stupid ideas and you can play, like if you were in a movie or Le Club des Cinq or whatever, and you just play together. And because you send letters and you create materials, things that were just in your head become reality, and you just can play with it. And to finish, I will tell you about our new project, which I like a lot. It started by a common feeling that we had. When I look at the sky, I told you I have a lot of feeling. But I realized when I was a kid, I told you my parents never did study, and I was not able to talk anything about stars and astrophysics to my parents. They were thinking I was crazy. I was really feeling like I'm alone. There is no one I can talk about these things I want to learn and I want to understand. I was feeling like I don't have families. I'm looking for a kind of spiritual family. And she was telling me the same. And we realized that there are many friends who have this feeling that they are alone in the cosmos and they cannot connect with the cosmos. And so we create these people which we call desiderate. So it's coming from desire. You see, desire is coming from the siderus, which means stars. Okay, so considerate is to navigate with the stars, and desire, desidere, is the feeling that you have when the stars are not here and you cannot find the direction with your boat because there is not star to find the orientation. You are completely lost. It's a disaster to be out of stars, disasters. So we imagine that there is these people and they want to reconnect with the universe. And we find a way, so we write this article about what we call, so it's in French and in English so that both of you, everyone can understand, but basically we have this new kind of humanity and they want to create an organic link with the stars. So the question is, how do you make an organic link with your body and the stars? With you, which is a finite volume, and the universe, which is infinite. What we know from mathematics is that you can take a sphere and you can put the inside outside, the outside inside. It's a very difficult mathematical operation. Can we take the whole infinity inside us? And this is what we try to do, and our idea is the following. We decided, and this will be done probably in a year or year and a half, that we will take a small piece of meteorite from the moon, so it turns out that I have some of them, and we will make a physical implant of this meteorite inside our body. And it means that the whole universe will be inside my body. My friend will do the same, which means that she will be inside me and I will be inside her, but everyone will be inside everything. So you see, like there is no inside and outside. After that, it's like topology. This is what quantum mechanics may call to be intricate or whatever. And so now we are trying, how do you do that? First, you have to find meteorites. Where is the best place to find meteorites? Is where you have crateriums and craters of impact of meteorites. So this one is in Chile, in Atacama. And so the first thing we did is to go to visit to this kind of craters and to look for people who are there. So see, this is us in the different place. This is in the States, so this is in Chile. And I even discovered that Baudelaire was from, you see, I discovered this text by Baudelaire is coming from the stone of evil, not the flower of evil, you see? And this is a poem I took from Baudelaire. I changed just a couple of words, like 5 or 6 words from the original poem by Baudelaire, from Les Fleurs du Mal, and it became Les Pierres du Mal. And basically, this is exactly what we want to describe. So we're just trying to play this game. So now we know that Baudelaire was one of us, and I'm sure there are many of them, because what I discovered is that there is also a dictionary here, see, with a lot of definitions of all what they want to do, what is desire, what is all these words, and explain. And when I read this dictionary, which is a little bit like the Khazar dictionary for those who know this book, you can understand by reading the definition what these people are looking at, what is their disease, and how they want to cure it. And this is exactly what we will try to do in the next year. So we go all over the world. This is where these people gather. They gather when they are telescopes because they want to understand about the universe. So this is in Chile. This one is in the States. And sometimes you found some people like that lying at the bottom of these craters of impact, just trying to reconnect with the whole universe. You see, it's like a new kind of humanity. Again, it's just a game, but this game allows us to question our position in the universe, question the connection with aliens. Aliens are very important. I don't know whether they exist. I hope they do. But even if they don't exist, we can question, if we just imagine they do exist, what makes us human? The time where we'll meet the aliens, how do we know that we are human? So what makes us common? So I think thinking about aliens is also a way to think about alterity and identity, which is something very important for us today on this planet. And this is the kind of question we want to ask with this project. And I realized, and I'm finishing in a couple of slides, if I'm too long, that this game, trying to use fiction and art to explain about science is not new. This is a text by Johannes Kepler, the astronomer. Somnium, le songe, the somnium astronomique, the astronomical dream. Kepler wanted to make people understand that the Earth is spinning and orbiting around the sun. He knew about it. He can demonstrate it from mathematics. He has the law of motion of the planets. The problem, no one understands them. Copernic did, Galileo, but it was a very few number of people. How can you make people understand that this is the true nature of reality? If you come with arguments, you will never convince people. At the time, he is not able to go to space, to make experiments, and he has to find another way. So he is writing this text, a 15 pages text, a fiction, in which he is traveling to the moon. He is going to the moon, and from the moon, he observes the Earth. He sees the Earth spinning, he sees the other planet moving, and everything becomes like a description of a normal trip. So basically, instead of trying to convince you by mathematical and physical argument, he wants to convince you so that you agree and you be in, I don't know the word in English, to make this argument your own, like a true feeling. And it's a very important thing because most of the things we find in laboratories, concepts about biology or the universe, if you want to explain them, they will seem to you that you don't understand them and it's out of your reality. The way to make them part of your reality is maybe to use fiction, science fiction, to make you adopt the concepts. And this is what I call paradoxical demonstration because we want to tell something to the larger public about what actually is correct by using fiction so that basically it's part of their own things that they can understand. So back to the moon. I told you the moon is so important, we have to go back to the moon. We have been on the moon, we have landed on different places. This is the last time with Apollo 17, we landed here on the moon. And about 2 years ago, I was joking with someone and I said, you see, we should put some piece of art on the moon because no one will be able to see it. That will be like the summum of art, something that we put on the moon. And after all, it was such a joke that it became a reality. I don't know why jokes became reality all the time. And so one of my friends, he went to see many people say, you see, we have to put something on the moon. And you know that there is a competition called the Google Prize to go on the moon and to make rover go on the moon. And there will be one which will be launched in a year from now, approximately. And with SpaceX, so with the firm by Elon Musk. And actually, we got for free 1 kilogram on this moon lander to put whatever we want on the moon. Okay, so that's nice because now we can do it. So the question is, you want to put something on the moon that will last there for hundreds of thousands of years because there is no erosion, there is no climate, there is nothing. It will stay there for hundreds of thousands of years. What do you want to put on the moon? So now this is what I'm working on. What to put on the moon. I have some ideas, I won't tell you. Because it's still work under progress and I want that we talk about it probably in a couple of months. What I can tell you is that it will be something that will tell us about what we know in the universe and on nature, what we know today, a kind of sense, this is what we call that sanctuary. But I don't want to be something dry in the sense, oh, this is what you know. Because if there are aliens and people from the future going there, they will know the same science as us. What is important is try to tell them what is our connection as human to this knowledge, to this scientific knowledge. What is water? What is water for you and what is water for people in Asia? This is the kind of question we want to ask. But the question is, how do you represent them? Because, of course, you will have to put drawings, pictures, whatever. So this is what we are trying to make at the moment. And hopefully, probably most of you can contribute because I think there will be a way that we send a lot of pictures, selfies of people all around the world. We want to show the diversity of humanity. You see, if you ask a kid to draw a human person, he will draw something very schematic, but we are all different, similar but all different. And we want to show the diversity of what is on Earth, because if we look at the diversity, we also have a way of what is the identity of human today, because of course with evolution in a couple of hundred of thousand years, they may still be humans. They will be so different from us because of evolution that maybe they will be alien to us. And this is very important to make the connection and see who we are. So this is what we are trying to do at the moment. But again, you see, it was just a joke at the beginning, and I don't know, some people take jokes for serious. It's very dangerous. So to conclude, I don't know what to conclude. To conclude, I talked about indisciplinarity, so I think it's very important that, of course, you are taught mathematics, art, science, music, whatever. They are boxes. These boxes are very important because it gives you concept and a way to think about the world and the disciplines and to make things. They are very efficient, but in other ways, they limit you because you have to stick to the logic of this field. What is important, if you have the possibility, is to be at the boundary between fields, because you will see the same problem from two perspectives, and sometimes you will realize the explanation does not match. And if you want them to match together, maybe you will have to invent something. Just think about quantum mechanics. We had waves, we had particles, and people were very embarrassed. If you read the paper by Einstein in 1905, it's very technical, but at some time it's very courageous. He said, everyone knows that particles are not waves. Let me assume this is not the case. Let me be free to tell you that it's possible. It's a thought experiment. Let me do that. And the paper was published. It was very good that it is published. But sometimes I'm wondering that if someone were doing that today, whether it will be published or not. So it's very difficult. Try to be free in some sense. If there are things that are important to you, let's just live inside yourself, and probably it will collide. You saw in particle accelerators, we take particles and we make them collide. And from this collision of two particles, a lot of new particles, sometimes unknown, are just coming to our universe. Let's do that. Take your own universe from your friends, and let them collide, and maybe there will be something new coming out of it. And I think this is probably very difficult to do. But if you like to play, and maybe you see, I show you some books for kids, if you stay like a children with always asking why. And I think the question why is probably the most important. And just to finish, I would like to say what it is to understand. If there is this very nice definition by Jonas Kohn, he's a philosopher, post-Kantian philosopher, and he says what it is to understand. And he says, if you want to, so it's written in German. I don't know whether it translates well in English, but in French it works pretty well. If you understand, you can catch an idea, which means you can take in your hand. To understand, to catch, is to see what is the limit of the things that you want to understand. Basically, what are the limits? But you can always ask the question, why is this limit? Why is this shape? Why is this boundary? And it means that whatever explanation you will give, there will be always a question, why is this and not something else? And he said, you see, there is a pressure of what you don't know and about the question why on what you know and what you explain. And this is like kind of an engine, and it tells you going forward to try to understand more and not just stay with what you know. You can be very happy about what you know, go to dinners and be very bright and tell your friends stories about particles and black holes and so on. It's very nice and very playful. But at the end, this is not what you want to do. You are very embarrassed. And I think if you want to do research, if you want to discover new things, you have to expose yourselves to be embarrassed. Say, that I cannot explain. That, you're right. It doesn't work together. It doesn't fit together. And this is because it doesn't fit that we have something to understand. So probably you have to use your knowledge not like to be comfortable in life, but to be very uncomfortable. Maybe that would be what you have to do. I don't know. This is what I'm trying to do. Thank you. Thank you.
Merci beaucoup. Thank you very much, Jean-Philippe. That was a brilliant conference about transdisciplinary and how could we mix science, how could we mix art, and so on. We don't have so much time this afternoon for questions, but if some of you wants to ask a question or two. The first question I have in mind is...
I put stupid question, which means that there is something I say in my conclusion. Never be afraid to ask a stupid question. The stupidest questions are the most difficult for teachers. We know that as teachers. So
I have one stupid question. What your colleague can think about you? Because you mentioned theaters and so on, what's happened.
But I grew old, and now my only answer is I don't care. And I don't care for two reasons. Because on one side, I'm doing my scientific work with papers and conferences and whatever, and no one can criticize that. It's just the pure standard scientific work. And no one can criticize this. And the fact that you are allowed to do something, I mean, some friends, they are doing biking or playing rugby or whatever. I don't question that. I can play with my friends. And this is something which everyone is allowed to do. So I don't care, actually.
Which is very important because you mentioned that you have to have the basics
Yes.
to be rigorous, to be pure scientific, to publish papers and so on. And then you can do whatever you want.
Yes, because people are tough. Colleagues are tough, and it's good they are tough. Whatever you do, even if it's pure science, if you have a new theorem, if you have discovered something, they will be tough, because of course they would have liked to find it in their way, or everyone, I mean, there is a competition if it's between people, and everyone wants to be the first. So people are tough, and each time you do something out of what is supposed to be the standard path, you will get criticisms. But you need to back up these criticisms to be strong in your own field, so that basically you cannot be attacked on the fact that you are not doing your own job, because this is what you are paid for. CNRS is not paying me for doing this. I do that in extra time if I want. They are paying me to do research on different topics, and this research is materialized by the fact that I write articles, that I go to conferences and so on, and that I have some kind of international recognition. This is what they want to know. The rest is basically part of me. Now they are just changing their view because they realize that we need to attract people to be interested in research and to be interested in science. So we have to do popular science, and there is some call from the world of art to discuss together. So I think it's opening, but it was not the case 15 years ago.
Thank you. We have a question just in the front of you, on your right side.
Yeah, just here. Just a quick question. On our first day, we had Michel Serres talking about science, and he told us that according to him, during the age of enlightenment, scientists were part of our society, and now not so much. Do you think that's true? Do you think it's relevant with the story you talked about your colleagues calling your work prostitution, and just your opinion about that?
Well, it's a very difficult question. I think there are different ways of doing science. You can be very technical and don't care about what you are doing. You know, you can demonstrate theorem and don't care about really the society in which you are living in. But I think that this is changing. It has been the time for a while. People wanted to discover these particles, do these telescopes, and it has really no applications for society. But I realize that things are changing because everyone is realizing that we have a game to play in society, and to see, you see, there are people who are questioning very basic things about what science has told us about the universe and the world, like Darwinian evolution, like probably global warming and all these things. And we have to defend what it is, what is a scientific method, what is something which is called science, what does it mean? And what can be questioned and what cannot be questioned because it has been proven. And it's very important because we have to tell people, and in particular politicians, how to take good decisions. Of course, if you go back to the time, let's say, of the French Revolution, and you see the debate at the assembly, you will realize that most people were really well educated in the science of their time. But now science is becoming so diverse that it's very difficult to know about biology and astronomy and everything. So if you want to take decisions, how can you be sure that you take decisions with the best scientific knowledge of your time? And I think now most of our colleagues, they have realized that they have a play to role as experts to help that. Because if you don't do, then people will think with ideas which are more than 1 century old, and they will make mistakes. So I think we have to be engaged in the world today as scientists. It's very important. I told you about, all this experiment with children and so on. This is the way to be engaged with the society. You have to go in the street, you have to talk to people, and there are many ways at every level to do that. And it's very important.
Maybe the last question over there. Yes, on your right.
You said that
right.
we have to be concerned about a lot of subjects and to know about biology, astrophysics, etc. But at the same time, it's become very difficult to be an expert because, for example, you're in Cosmos and you have to know much more than Einstein, for example. And I think all your colleagues, you know more than Einstein. So do you think that, my question is, do we have the time to learn all this and to be expert in several areas? Or our life are now too short to be good?
Yes. Knowledge is growing, so it seems that you have more and more things to learn. The point, of course, is that most people who are working on general relativity today, they know the theory in a way which is much better than Einstein because it has been really understood, it has been simplified. So when you discover something, usually you don't have the good tools. I show you with this Maxwell equation, like a long page of equation or just a couple of symbols. When you just see that it's a couple of symbols, you realize that it's very simple to learn and to understand, once you know the mathematics, of course. So it means that many theories you can learn very fast. And it's because we have education, and all theories, they have been, simplified in the way they are expressed and in the way they are taught. So basically, it's much more faster to learn general relativity today than it was in the 30s, for instance. And when I was a student, this is something that you were just studying when you were in Master 2, and now general relativity, some students start that when they are in license. See, and so this is why you can take the most difficult subjects, and because you are doing popular science, because you are working on the way to teach something, you can learn them faster. Of course, you cannot know everything, and I think the idea that they are universal people, that it existed before, is something that do not exist anymore. But the more you grow old, the more you read, and I think the more you study, the more you read fast, and you can really catch what is the important point. In every field, there are technicalities which are very difficult to learn if you really want to contribute to the field. But if you want to know what is the important conclusion of molecular biology or whatever, you can grasp them even if you are not a pure technician. And I think now there are so many people trying to explain that it's possible not to be universal, but to have a fair idea of what's happening in many fields. It takes a lot of time, but I think it's a nice goal.
Thank you very much, Jean-Philippe. Thank you very much, Jean-Philippe Uzan, for being with us today. That was a great pleasure, great inspiration.